Hello, everyone, and welcome to our webinar on analysis of the evolution of a contamination plume using Visual MODFLOW Flex. This is part of our international webinar series 2020. So going to today's topic, so why model? So hydrogeological models facilitate the assessment of natural processes that affect the flow of groundwater and the transport of contaminations in complex environments which involve the physical process that occur in the hydrogeological environment. So we are looking at a groundwater flow controlled by advection, but also in terms of contaminant migration in the subsoil, things like dispersivity, diffusion, which are relatively complex mechanisms to be dealt with only analytically. And of course, when we do 3D numerical models, we are thinking about the spatial distribution of these physical properties and as well as boundary conditions. And we are interested in looking at the effects of the flow system over time. So in a model, we can build in all these complexities and calibrate it to existing conditions or to recorded historic conditions. And then use that model to project future scenarios and assess what may happen in the future, depending on the problem that we are addressing. And of course, the better we represent the groundwater system, the better our predictions will be. And of course, as well, we should never look at any software as a black box. So data, let's say solid field data, is essential for developing any model, as well as professional judgment, what we commonly refer to as reality check. So it's always important to look and think about what we are doing when we are developing any sort of numerical model. And of course, models can be used to simulate a large range of situations related to groundwater flow, specifically when we are talking about Visual MODFLOW Flex. So we can use it to refine our understanding of the hydrogeological context that's being assessed, being on a small scale, for instance, in industrial property, or if we are looking at large regional aquifers. We can assess things like aquifer abstraction or aquifer exploitation sustainability. In other words, how much water we can get out of an aquifer system without compromising its long-term ability to supply that water that's being required, which comes into the impacts then that we need to look at related to aquifer exploitation. In terms of water quality, this is then when we are going to look at things like transport of contaminants on subsurface. So there is an enormous range of situations where groundwater may be impacted, be it in an industrial context, say from organic compounds, or in a mining context, for instance, leachates from tailings that infiltrate the subsurface and affect the quality of groundwater. We can not only assess how the quality of the water is going to vary over time, presuming we understand its source and how that physical system works, but we can also test, design and test physical intervention systems, what we refer to as remediation systems, from anything from reactive barrier or a pumping well to the injection of some substance, some chemical substance that will react with the contaminant and neutralize it. So there is a number of things that we can do, both in terms of assessing water quantity and water quality. The usual workflow, of course, we are always going to start with some data gathering. So we do, let's say, a preliminary hydrogeological assessment and try to obtain as much data as we can from that environment, from aquifers, rivers, springs, climate data, everything that really is going to drive the way that system operates. We bring that into a conceptual model where we start to sort of put our conceptual understanding of the system in a more graphic format. And at that stage, when we are reasonably confident that we understand that natural system conceptually, then we can start thinking about generating a numerical model and start working on that model in terms of calibration before we can do any projections. Depending on what we are looking at, in this example, we are looking at a well field, so we are thinking in terms of abstraction rates and spacing between wells. So our numerical model may be, normally will be the basis for some sort of system to be implemented on site, especially if we are talking about groundwater abstraction. Then any system, any projections we make are always going to involve some level of uncertainty. And then we need to monitor how that system is going to behave, to monitor if it's going to reproduce what we have projected. And if not, we'll have to adjust it and update our conceptual model. And that's sort of a full circle that we go there. And at the center of all that, of course, we need to have some sort of system to manage the information that we are gathering. And this is where a software like HydroGeoAnalyst, which is also developed by Waterloo, also comes into play, where we can store and organize all the data efficiently and use that data for different applications, such as a numerical model. So we should always have some sort of system to keep the information up to date and organized. This is a sort of industry standard flowchart that shows the process of developing a model. So we always start by thinking about what the objectives are. So what do we want that model for? Because that's going to have direct implications, for instance, in the model scale. That means what's the area that's effectively going to be modeled. And from then on, we start doing the data collection, building the conceptual model. And this is sort of the stage where we conceptualize the system, the natural system that we want to assess. Once we have a robust conceptual model, then yes, we'll move to the numerical part, and we'll start that normally by designing the model grid, assigning boundary conditions, parameters, properties, and doing the model calibration and validation depending on the amount of monitoring data that we have. So this would be the model development stage. What we will see with Visual MODFLOW Flex is that this conceptual model stage has been brought into work routine, whereby at the end of this, we actually already have a lot of the information that we are going to use in the model development. And also, when it comes to the design of the model grid, we are already going to have our conceptual model built in this previous stage, so we can actually test different types of grids and modeling approaches without affecting our conceptual model, which is really a big difference on what Flex does in relation to other tools that are available for modeling. Once our model is calibrated, then we are going to move into this third phase, which would be the sort of the predictive or scenario analysis. Here, we do a sensitivity analysis, which is essentially varying the values of the parameters that we have inserted in the model to see what really controls the flow system in our model, and to see if we have enough data to be confident that the properties or the actual parameters that we are using are the ones, in fact, that represent the system in the field. And as mentioned previously, we are always going to have some level of uncertainty. So the modeling process is always going to be a sort of a circular process, whereby as we get more information, we update our conceptual model and return to these stages. Here at this third phase is where we do our predictive simulations and see how these results are, and this is an important part to make what I mentioned previously of the reality check, to make sure that what the model is predicting makes sense in the real world, especially in terms of mass balance usually. So it's always important, you know, at each of these question points here, it is important to think about these reality checks. But anyways, that's sort of the overall modeling process charts. So I just wanted to make this brief introduction before we move into the example using Visual MODFLOW Flex. Okay, so let's have a look then at the Visual MODFLOW Flex interface. So I'm just going to start here from, well, this is the opening screen for Visual MODFLOW Flex. So what we have here is sort of some standard main menus, and we have a window which is the data explorer. This is where we bring all the data that we are going to use in the model. That's where we bring it and organize it. And the model explorer, which sort of records the steps that we take when developing the model. So let's just start by creating a brand new model. So let's just take this. Let's call this our webinar model. And okay, let's create a folder for that project. I'm just going to select a different file, a different place to put that model in, my C drive and webinar. Okay. For now, we'll just start with the default units, and let's just okay this. Okay. When we do that, the first thing that comes up on the screen is that we can select between developing our conceptual model, or we can move straight into the numerical modeling. Well, in our case, we want to start from the conceptual model itself within Visual MODFLOW Flex. So we're going to select this option. And when we do that, okay, then our conceptual model workflow is going to appear here. So this is a list of all the steps that we need to follow here on this window. And we can only move to the next step when we have completed the information that we need to insert from the previous step. So for the moment, let's just think in terms of flow. What I'm going to do for this example is move our date here to the 1st of January 2000. So let's just do that, because we are going to count our simulation time from this period here. So this is the main thing we are going to do now. Just leave everything on the default, and we'll make the adjustments as we follow. Okay, and we'll start with, well, the flow type is going to be saturated and constant density, and of course, groundwater flow simulation. Then I'll just select this this next step, and here is where we can start to bring data into the model. So we have 3 options here of importing data that has already been being prepared previously, and we can create new data. So let's start by importing the data that we need to import. Let's start with some polylines. We have several polylines that we need to import. So let's start with the model limits. So it's just this polygon. Sorry, this is a polygon called boundary. So let's just next this. Okay, and finish. Okay, if we come here and we open a 2D window, we can already see our model boundary. So in this case, it's just a square area, but we'll see how we're going to use that further ahead. Also, let's import now, yes, the polyline, some polylines, which will be our constants, our boundary conditions on the east section of the model. So just call this constant head east. We'll just finish that, and let's do the same thing for the second. So again, polyline, source file, constant head west. Let's open it. Next and next. Yes, and yeah, now it's okay. And let's do the same thing with the river that is going to cross our study area. So we'll just come here to this river main, open it, and again. Okay. What else do we need to bring in at this stage? Yes, of course, we need to bring in the surfaces that we are going to use to create our geological layers. So let's select here surface, and then it's going to show us the ground surface, which will be equivalent to the topography. And we'll import that. Let's also import the top of the second layer or the bottom of layer 1. So in this model, we are going to have essentially 2 geological layers. And let's import the base of this second layer. Okay. Okay. So once we've imported this sort of initial data, let's move to the next step and start building our conceptual model. So what we are doing in this workflow is really to build the 3D hydrogeological concept that we want to use in our model. So I'll just keep the full name. First thing we need to tell the software is the model limits. So I'm just going to select the boundary polygon that we imported before. Let's save this. And when we save this, see that it opens already, starts to show some elements here on the model explorer. Now this is just to define our model limits. So the next step will be to define our model structure. And the model structure is really going to be the surfaces, importing the surfaces that are going to create the top and bottom of our layers. So let's start with the ground surface. So just select ground and bring it here. So this is going to be erosional type surface, as the topography always is. And then I'll move to the second layer or the second surface. I'll bring the top of the second layer, just leave that as conformable. And I'll move and do the bottom of the second layer. And again, I'll leave that as conformable. So once we do that, let's just save this. And if we want to see what we have here, we can come and create a 3D window, and then we can well, we can actually, instead of doing this, we can actually see here our horizons, our 3 horizons. Just put the vertical exaggeration here to help us see a little better. But you see that here we already see that sort of, a river topography come here in the middle. And these are the surfaces that are going to form the 2 solids that we need to define for the for the hydrogeological units. So we'll go back to the conceptual model menu, and now we are going to define our property zones. And we'll do that by selecting here on the Model Explorer first zone. So let's put here use structural zone. We'll bring that zone 1 to structural zone, and here we can already insert our hydraulic parameters. So in this case, the hydraulic conductivity will be 410 to the minus 6, and that's for Kx, Ky, and Kz will be 1 order of magnitude lower. Okay, so we save that. Okay, we can adjust that later. And then let's, again, select use structural zone. Let's bring in our second zone. And here we will assign the hydraulic conductivity of 10 to the minus, or 710 to the minus 5, 710 to the minus 5, and on the KZ we'll put 710 to the minus 6. Okay. Now let's save that. And when we save this, see that it created 2 property zones. So if we come back here on our 3D viewer, we can already see the 2 layers that we created using those 3 surfaces. Okay, so these are our numerical layers. Let's move to the next step. In the next step, we'll find the boundary, or start defining the boundary conditions. So let's do that. And let's start by defining our 2 constant headlines, one in the east and one in the west of the model. So let's just call this constant head east and select the line that's going to represent it, and then we'll select next. And for this boundary condition, we are going to use a constant head of 347 meters throughout the simulation time. So, okay, so we have that. Let's go there again and define another boundary condition. Now we are going to define constant head west. I'm going to select our polyline, bring it here. You see that we use these sort of data elements to construct our model. So it's very important to actually prepare these files in advance before start building your conceptual model. So again, let's bring this in. On the west, we're going to have a hydraulic head of 325. Yeah, and so this is what it's going to be here at this stage. And then let's define also our river. So we are going to have a river that crosses the area from north to south. So let's just call this river main, and we'll bring it from there. So let's that's okay. And let's just put next. The difference here is that we are going to apply different heads in the river, in the northern and southern parts, to represent this sort of gradient that it has between those 2 areas. So in the northern, we're going to have an elevation of 335. The bottom will be at 333. Riverbed thickness of 1. River width of 50 meters, and a riverbed conductivity of 10 to the minus 2. Okay, so let's move to the downward point now. So it's going to have an elevation of 334. to 1 meter 50 and 0.1. Okay, finish. All right. So if we go to our 3D viewer, let's just take those horizons from there, and we want to see. Okay. Our boundary conditions. Okay, maybe 3D is not the best way to look at that, but let's look at 2D then. Then we have a constant head on the east, constant head on the west, and a river cutting through the middle. And yes, let's import also our satellite image for this location. So we just select the option map, and we'll bring our satellite image to the model. So let's next this. Okay, I've already selected previously the 2 points of interest. Just put this so it reads the georeferencing points. This is a step to georeference the image. Okay, let's just finish it and see how it looks. Okay, so this is what it looks like. And if we want to see our river, okay, so this is a river cutting right through the middle. Okay, so this is pretty much the basis for our conceptual model. We have essentially we have created our hydrogeological layers, and of course this is a simple model with only 2 zones, but it could be a much more complex model depending on the problem that you're working with. And now is where we select the grid type. And this is an interesting part, because we can select a finite difference grid, which is the standard MODFLOW grid. We can define a finite element mesh, and this can be exported directly in a format that you can read into VFlow if you're also working with that in your modeling. And we can define unstructured grids. So we have this Voronoi type mesh, and we have this Q grid type mesh. So let's just make a first try. As a matter of fact, let's do the standard model. That's the main part of our example, which is the finite element, the finite difference grid. And let's apply a number of 100 rows and 100 columns. And okay, we are not going to rotate the grid at this stage. So let's just call this numerical grid FD for finite difference. And next, and if we put some exaggeration here, okay, then we see the sort of geometry that we have developed in this model. So let's just finish this. Oh yes, and then here we have the option of creating a deformed grid, uniform or semi-uniform. So you can also play with those parameters here. But let's just finish and create our standard grid. Well, once we create our grid, then the next stage will be to convert our conceptual model to a MODFLOW model. So let's do just that. Okay, let's convert to a numerical model. Okay, so 2 things happen when we do that. First, a new workflow appears here, which is the numerical modeling workflow. And also the whole workflow for the numerical modeling also, the elements involved in that also appear here on the Model Explorer, window. So let's just have a quick look at our numerical model. So, okay. So in terms of properties, let's check the 2 layers that we created. And here, if you recall, this was supposed to be 4⁻⁻⁶ as well. So I'm just going to adjust that. And if I push this assign to column option here, then it's just going to replicate that value for all the cells in that group. And so this is layer 1 in the model, and on our second layer we can see the values that we've inserted in the conceptual model workflow, so they are already here. So basically we are just doing a quick check. Let's do the same thing with our boundary conditions. Here we can see our 3 boundary conditions. One tool that we can use here is this cell inspector. So let's just use the cell inspector to see how our boundary conditions are set. So let's start with the constant head east, and then we see here starting ending head at 347. Okay, so that's exactly what we have assigned in the conceptual model workflow. We do the same thing now. We constant head west, we see the 325, and we see this river in between. So if we go up there in the river, we are going to have a head of river stage of 335, and if we come down here, we're going to have a river stage of 334, which is exactly what we have assigned. So let's just okay that. So our boundary conditions are okay, and we can move to the next step. And here we can either move straight away to the simulation stage, but we can also define particles, and we'll see that in a moment when we look at the unstructured grid alternative. We can define our zone budget zones. So for those of you who worked or who are used to work with the classic version, you know, this is the option, or this is the menu where we can set up our zone budget zones. And we can also define our observation wells if we are doing model calibration. So let's just, for this example, let's just move straight away to the single run option. Here we can choose between the single run, which is just a normal model run, or we can use it to set up a test run if we want to. At this stage, in this example, we're only going to do a single run here. So let's just select that. Okay. And here it shows us which flow engine we want to use. So we have all these options here. So I'm just going to keep it on the default of USGS MODFLOW 2005. If we had set up our zone budgets, then we would select this to run the zone budget simulation. But again, for this very simple example, we'll just do the standard MODFLOW run and move to the next step. So here in the next step, it's the translation step. So this is the stage where MODFLOW is going to read all the files, or all the input files that we have set up by inserting our properties and boundary conditions, etc. And we can also select our solvers here. So, you know, you can come here and select any of these solvers. I'll just keep the default one for now. And you can also set all the internal parameters for that solver. And you have other specific settings for your MODFLOW packages. So recharge, lake, layers, etc. So let's just translate that. Okay. Okay, so this is an interesting one. I left the initial heads at their standard default value, so I actually forgot to set up the initial heads to an elevation which is above the elevation for the boundary conditions. So it's all set at 100 meters. So it cannot work because we've set up our boundary conditions to an elevation of 350. So let's just start with, say, or 347. Let's just start with initial head of 350, and let's just replicate that to the entire model domain. Okay, and then we can go back straight back to the translate option and do a new translation. So now it's not going to give us any error, and we can actually move to the next stage where we are going to run the model. So let's just push run, and very simple model. It runs very quickly. And then we have the options of viewing charts and maps. So let's just see this option of viewing map. So basically what we see here is the hydraulic head map. We can also turn off the grid to make it easier for us to see. If we want, we can see where our river is passing. So it's just doing this here, and that's why we see this little bump here in this isoline. And the same way we see heads, we can see, for instance, the water table, which is in this example also is not going to vary much. And then in charts, we have a number of options. It's telling me that I have no observation wells, so it cannot show me any calculated versus observed heads. But another thing that we can see here is the mass balance for the entire model. And so let's just, okay. And then, yeah, then it's just going to tell us water in, water out by which boundary conditions, and this shows that total amount in is total amount out. So we don't have a mass balance error, which is important. So again, this very quickly is how we would set up and run a simple numerical model. Now I'd like to go back to our conceptual model workflow and show you, okay, so what if I wanted to create a different type of grid? Let's say if I wanted to work with a Voronoi grid. So let's just select this one. So we'll call this, we'll just leave it Unstructured Grid 1. In this case, the Voronoi grid or mesh, it's going to use certain elements from our model. So basically what we have here are all the sort of linear features from our model. But if we had wells, for instance, we could also have those here. And it's just going to create the mesh around those elements. So let's just give this next. And then we have some options for creating the grid. I'll just leave it all at default, and then I'll just select here, generate. And okay. So this is our Voronoi generated grid with 2 layers. I'll just finish this and we'll have a look at that grid. Okay, so 2 interesting things here. One is that in our model explorer, now we have not only our numerical grid finite difference, the one we did before, but we also have a new unstructured grid. Now, what we need to do here is to convert, because all we did now was to create the grid. So now we need to convert this to an actual numerical model. So let's convert this to a numerical model. And then we are gonna essentially follow the same steps we did for the finite difference grid. So let's just do that quickly. Okay, and you can see that the grid the grid has, let me just switch that off. It has been already refined around the river and the edges of the model, which is where we have those linear elements that were used to condition the creation of this numerical grid. If we go to properties, they are already going to be there the same way we saw for the finite difference. So this is very interesting, because essentially you have one conceptual model, and then you can try 10 different grids if you like, and actually run them fairly quickly. So our boundary conditions will be here, our two constant heads, and if we select river, okay, so we have our river here. And if we did the same, the same inspection that we did before, and let's say we just select one cell here, okay, so it's showing again our river stage and so on and so forth. So you just select, you just click where you want, and it's going to give you the boundary conditions at that location. So our boundary conditions are fine, and we can select our next step. And you see here we go back to that menu where we have all these options. In this example, I'm just going to well, actually, I'm going to import one polygon that have not imported before, which is our contaminant source area that we are going to see for the transport model. So let me just bring that in, source area, okay, and next, and next, okay. And let's define a few particles. So I'm going to switch on my source area. So here we have the river, and here we have our contaminant source area. As a matter of fact, I should have, let's just do that. Let's just do that very quick. I'm going to create a third grid, but using the contaminant source area as the as one of the features to be refined around. So I'm going to go back to the conceptual model, and I'm going to create again. I'm going to select again Voronoi grid. But now I'm going to add the source area as one of the elements for the grids to be generated around. So I'm just going to do this very quickly. Yeah, you see that now we're going to see this better in the next screen, but we can already see that it's being refined around our contaminant source area. So let's just finish that. Yeah, there it is. And let's convert this to a numerical model. Now we're going to have our unstructured grid run too. We know that our properties are okay. Our boundary conditions are okay. And then in our next step, now let's select a okay. So let's select. Let me just check something here. Yeah, okay, no, that's fine. Let's create some particles around our contaminant source area. So that's the source area. And now let's assign some particles using, well, let's use a data object, which is going to be the source area itself. So let's just select that. Okay, and we'll just set some forward particles, and let's just okay it and see what it does. Okay, so it basically created a whole bunch of particles with a spacing of 10 meters from each one. And if we zoom in, we can actually see our particles were created. Okay. So let's say that we just want to have a first look at our flow, and we'll move to the next stage, and we'll select a single run. Now see that now we have the particle tracking option here. I just need to check in the properties if our initial heads are okay, because they may not. Yeah, so we need to set these again to 350. Okay. Okay, and now we can go back to our single run. Select USG MODFLOW and mod path. And if we move to the next step, I'm not going to fiddle with any of the settings for this. So let's just translate this. Okay. Once it's translated, then we can move to the next stage and run the model. So let's just run it. Okay, so it looks okay. Let's have a look at the maps. Right, here we see our flow fields, but we don't see our particles. So let's switch on this source area of ours. It's just there, and now let's show the particles. Okay, so we see it's just doing exactly what we expected. If we want, we can open a 3D window, and let's see, we can put our select heads. Okay. Let me switch on the, okay. So now we can see the numerical grids, and we can see the particles moving from our contaminant source area to the river. Of course, you can play a lot around with the settings for for these things to look nicer. But just to show you how simple and how quick it is to take one conceptual model and start generating grids one after the other. So here we conclude the flow part of our example. Now let's look at the transport stage. So we'll just go back to our finite difference model. I'm just going to minimize the two unstructured grids that we worked with just now. And I'm going to go back to modeling objectives. And now here, I'm going to activate the transport option. And we are going to use a simple linear isotherm. So this is the sorption model, which is essentially going to control the retardation of the contaminants in the aquifer in relation to the groundwater flow. And I'm going to call our contaminant just chemical species 1. And let's say that this contaminant is going to have a distribution coefficient, or KD, of 110 to the minus 9. And an initial concentration of 0 throughout the model domain. And here we will just use the default values, but you can see that here, for instance, you could change the bulk density of your aquifer if you wanted to. Okay, maybe we should save this now. As a matter of fact, you should always be saving this when you're working with the model. And now we are going to attribute some contaminant flow properties. So let's start by just having a look at the initial concentrations. So as I mentioned previously, our aquifer is going to have an initial concentration of 0. Okay. And we'll leave the dispersion at the default. The dispersivity the default longitudinal dispersivity is 10 meters. So we just leave it at that. Now, if we come here on the Model Explorer menu and come to dispersion and right click on it and select the dispersion parameters, then we can see how the relationship between horizontal and longitudinal dispersivity and vertical and longitudinal dispersivity is set up. So one is 10% and the other one is 1% of the longitudinal dispersivity. In this case, diffusion is not going to be important in our example, so we just leave that at 0. Okay. What other? Okay, bulk density, we saw that it's being set up at 1700 kilograms per cubic meter for the entire model. And the species parameter is going to be the KD value that we've just set up as 110 to the minus 9. Okay, so our properties are looking good. Our boundary conditions now, what do we see? Our flow boundary conditions, but we need to set our transport boundary conditions. And the main transport boundary condition in this case is going to be the concentration of our contaminant of interest, chemical species 1, at the source area. So I'm just going to zoom here to the source area, and I'm going to select constant concentration, and I'm going to assign a number of cells. So let's say that we are going to assign these 4 or 5 cells, or well, let's call it 6. Oops, here as the contaminant source area. So just finish this. Okay, so this is going to be constant concentration 1. And I'll just next this. And I'm just going to address a constant concentration in this area of 5,000 milligrams per liter of our chemical species 1. And I'll replicate that for the 6 cells that we have selected as our contaminant source area. Okay. Once we finish this, we see here that it's been set in layer 1. And if we wanted to use our cell inspector, again, for the boundary conditions, we can click here and we can see constant concentration 5,000 milligrams per liter. If I click on the cell next to it, it's not available because there's no boundary condition there. So we'll just, let's just close that. So this is the main, let's say, change that we are going to do for the transport simulation in terms of boundary conditions. And let's just move to the next step. Again, we can define particles, budget zones, we can define observation wells by importing data from Excel files, for instance. But for the sake of this example, let's just move to the simulation run. Again, we have the pass option, but we are going to do a single run. Okay. Now see that we have the option here to run the transport engine. So it's been activated once we changed our modeling objectives up there. So we'll just select that and let's move to the translation part. Okay, so here again, the same way we have the options to select solvers and settings for the MODFLOW simulation. We have the same thing for the transport model simulation. So let's just look at the solution methods. We are going to use these upstream finite difference, and let's use also this implicit GCG solver. And here we are just going to make one adjustment within this multiplier factor, which is related to the size of the time steps that's going to use to solve, to do the transport calculations. And yes, let's change also the maximum step size to 200 days. And those should be okay. Let's actually save this again. Now, output control is where we define the results that we want to see. So let's determine for the transport model a simulation time of 7,300 days with a maximum number of transport steps of 5,000. We'll just leave those as they are, and let's define the output times that we want. So let's just use, I'm just going to create a few lines. So we want to see the results after 1 day, after 2 years, 4 years, 10 years, 15 years, and 20 years. And I'm just going to delete this. Just going to delete that last line. And okay, now we save this. And and now we should be ready to run our transport model. So what we need to do here is to do the translation. So now both MODFLOW and MT3D are going to read all the information that we have inserted. Okay, and then we are ready to run our simulation. So I move to the next step. And here we have the two tabs that we are interested in, MODFLOW and MT3D. So let's just run that. First we will run MODFLOW. And then the transport model, MT3D. Okay, so both finished. Let's have a look at the maps. Okay, so what we see here is basically the results from our flow model. Just the flow field as discussed previously, but now what we really want to look is our concentrations for our plume. Okay, so if we go back here, time 1. So what I'll do here is I'll just improve the visualization. So I'll move here to the 3D view and select that one off. Okay, so just to start with, let me just remove these ISO lines. Okay. Okay, show ISO lines. We don't want to see that, so let's. Okay, well, they're still showing. Let's prepare our map for a good visualization. So. Okay, so we'll just switch this one off. In color map, we are going to show color map, and we're going to look at the layer. And I'm going to set up a lower cut level here of 100 milligrams per liter, and I'll use that. Okay, no ISO lines. Let's remove the 3 slices. So these are just settings for us to have a better look of the results. So let's just okay this. Okay, so this is our plume here at time 1. What I'll do is I'll put our satellite image underneath it. Okay, so this would be us then looking at our simulation results. So this is what it is on the first day. Then after 2 years, and after 4 years, and in 5 years, actually, it's already reaching the river. Okay. Of course, this is for a minimum concentration of 100 milligrams per liter. So if we actually let this thing run for the entire time, it's not only going to impact the river, but it's actually going to also flow to the other side, considering that the original groundwater flow here would be from sort of east to west. The other thing that we can do is in our options here in settings, we can visualize the time steps. So let's just put show timetable, and we can actually put the actual date of the step that we see on the screen. So this would be at the end of the simulation, remembering that we started in the year 2000, and then as we move, it kind of shows us in absolute terms where we are. So this is what we had for today. Thanks for your attention and participation. If you have any questions, I'll be happy to answer them. Thank you.